Hi everybody, so we're going to continue with Chapter 1, Algebra and Function Basics, specifically with Topic 1.5, Transformation of Functions. So on this first slide, you're going to find a series of very common functions that some people like to call parent functions. And you have to become familiar with them. So the first one is a constant function, which is just a horizontal line that depends on the value c, which is constant. We have the identity function, which is f of x equals x, and it's this line that goes right through the origin, forming a 45-degree angle with the x-axis or any other axis. We have the absolute value function, which is the v-shaped function. We have the squaring function, also known as the quadratic function, f of x equals x squared, which is this parabola. We have the square root function, which is this nice smooth line that has downward concavity and that rises slowly. And then we have the cubing function, or the cubic function, f of x equals x cubed. On the next slide, you're going to find a couple more of these parent functions, which are the reciprocal function, as you can see there, 1 over x, and the inverse square function. So here's something very interesting. Notice that the inverse square function is 1 over x squared. Because x is squared, it means that this will always be greater than 0. And that is why if you look at the reciprocal function, the left portion of it, the portion before 0, is negative. But in this other function, 1 over x squared, this portion is now positive. So first we're going to look at the vertical and horizontal translations. And on this graph, which is figure 1.29 to the left, we see in blue here, the function f of x equals x squared. And in red, you see the function x squared plus 3. So this is a vertical translation of 3 units up, or up 3 units. Notice that all the x coordinates remain the same, but the y coordinates are increased by 3 units. So notice that the point 1, comma 1 becomes 1, comma 4, or negative 2, comma 4 becomes negative 2, comma 7. And this fact is very important because in some IB questions they will ask you for transformations of this sort without giving you the functions themselves, but you know that when there is this translation in the vertical sense, you have to think of it as f of x plus or minus a constant. And this is going to shift all the y coordinates up or down. To the right, we can see f of x equals x squared translated 2 units down. And notice that we see the same pattern. In this case, all the y coordinates move down 2 units and the x coordinates remain the same. So we see the example of 3, comma 9 becoming 3, comma 7, or negative 2, comma 4 becoming negative 2, comma 2, and so forth. Next, we're going to see the concept of horizontal translations. So for instance, if you want to translate or move x squared 3 units to the left, you would have to rewrite that as x plus 3 squared. So in this case, this is only going to affect the x coordinate. Now the interesting thing with the horizontal translations is that they move backwards, so to speak. So if you want to move it 3 units to the left, you have to make it x plus 3. Notice that the 0 of this function on the x-axis will be negative 3, as you can see here. It used to be 0, 0, comma 0, but then now it's negative 3, comma 0. So that is why it will move backwards with respect to the sign you use. You can see that also in figure 1.32, where x squared is translated 3 units to the right. And here they say x minus 2, so it's not 3 units, it's 2 units, so this is wrong. 2 units to the right, and x squared will become x minus 2 squared. Notice that the 0 was 0, 0, but now it is, in this case, 2, 0. So the only thing that you have to remember with this horizontal translation is that it affects x only, and it moves contrary to the sign of the number that you placed next to x. So x minus 2 moves it 2 units to the right, x plus 3 moves it 3 units to the left. Notice again that the x coordinates are the ones that change. So for example, 0, 9 becomes 3, 9. Negative, or backwards actually, 3, 9 becomes 0, 9. Negative 2, 4 becomes negative 5, 4. And same with the graph to the right. So negative 2, 4 becomes 0, 4, and 3, 9 becomes 5, 9. So next, we're going to take a look at example 1.21. And it says the diagram, or the diagrams show how the graph of y equals square root of x is transformed to the graph of y equals f of x in 3 steps. For each diagram, A and B give the equation of the curve. So for A, it's simply a translation of 3 units to the right. So just remember that we would have to affect x. So that means that f of x equals square root of x would become square root of x minus 3 because it's to the right. For B, we have that the curve also shifts up one place. So notice that this now becomes f of x is equal to square root of x minus 3, but we have to add that shift up, which would be positive, and in 1 unit. We continue with example 1.22. And it says, write the equation of the absolute value function shown by figure 1.33. So the absolute value function is f of x is equal to the absolute value of x. Now, if you recall, that function is shaped like a V. So it has the vertex at 0, 0. So let's look at what happened to the vertex. The vertex, the new vertex, is at minus 2, minus 3. So that's the new vertex, minus 2, minus 3. The original vertex was 0, 0. So this implies, this minus 2 implies 2 left, 2 to the left, and this negative 3 implies 3 down. So we have to shift it 2 left and 3 down. So remember that the horizontal is going to affect x only. So we have to go f of x would equal absolute value of x plus 2. Because for x, we have to do it backwards, right? So x plus 2 shifts it 2 units to the left. And for y, we would use the same sign. In this case, 3 down would be minus 3. So this would be the absolute value function for figure 1.33. In the next slide, we're going to see the topic of reflections. So first we have figures 1.34 and 1.35 that show the graph of y equals minus f of x. And minus f of x is obtained by reflecting the graph of y equals f of x in the x-axis. So notice that when we say y equals minus f of x, what we're saying is reflect every y value or do the opposite of y. So notice that if in the original function y, the y coordinate was 9, for minus f of x, it's going to be -9. Notice that the x-coordinate is not affected. So by doing that, you're going to get a reflection across the x-axis. Same for this coordinate. X is 2 here and also here, but 4 becomes -4, and that makes the graph reflect across the x-axis. And even if you have a point, let's say, below the x-axis, its reflection would be above the x-axis. So this was obviously here. F of A was negative, and minus a negative would be positive, so that's why it reflects up towards the positive part of the graph. So here we would have a positive y coordinate, which now would become a negative y coordinate. Notice that all the x's remain the same, so A still is A and B is still B. In the following slide, we're going to look at examples of a reflection across the y-axis. So in order to reflect across the y-axis, what has to change is the x-coordinate. And this is done by simply putting a negative sign in front of the x. So for example, in figure 1.36, to the right in blue, we see the graph of y equals square root of x minus 2. So the reflection of this across the y-axis would be square root of minus x minus 2. And notice how the y-coordinates remain the same, and it is now the x-coordinates that are opposite each other. So here in blue we have 11, 3, which reflected would become negative 11, 3. 6, 2 would become negative 6, 2. In general, we have what the rule is. So the rule is, if you want to find the reflection across the y-axis of a function, what you do is y equals f of x should become y equals f of minus x. So notice that this is done by putting a negative in front of every x in the equation or in the function. So to the left, you see the general rule. The graph of y equals minus f of x is obtained by reflecting the graph of y equals f of x in the x-axis, or across the x-axis, I would say. The graph of y equals f of minus x is obtained by reflecting the graph of y equals f of x across the y-axis. So now let's take a look at example 1.23. And it says, for g of x equals 2x cubed minus 6x squared plus 3, find A, the function h of x, that is the reflection of g of x in the x-axis. So that means the reflection of g of x across the x-axis. So that means that h of x is equal to minus g of x. This would be the reflection across the x-axis. So what we do is that we just put a negative sign in front of the function g of x. So that would be minus 2x cubed minus 6x squared plus 3, which is simply going to be minus 2x cubed plus 6x squared plus 3, or minus 3, I should say, sorry. Minus 3 here. So it just means opposite signs for everything. For B, they want us to find P of x, but P of x is a reflection across the y-axis. So that just means G of minus x. And that would be then 2 times minus x to the 3 minus 6 times minus x squared plus 3. And then what we do is that we apply the signs for, or the rules for signs, right, and powers. So this would be negative 2x cubed, because this is odd, so this number, whatever it is, will be negative. Then we have minus 6 x squared. This will not be positive because anything squared is positive, plus 3. So P of x, this would be the reflection across the y-axis, and H of x would be the reflection across the x-axis. And we're going to see that graphically next. So here we are with the graphing calculator, plugging in the functions. So first we have that this is g of x, and this is the reflection across the x-axis, or minus g of x, which is h of x. So we're going to hit the graph button, and we're going to see what happens. So we graph, and there you are. Notice that you have a perfect reflection across the x-axis. So next we're going to graph g of x and the reflection of g of x across the y-axis, which is g of minus x, which in the example is p of x. So we're going to hit the graph button here and see what happens. So there you go. You can see that you have a graph that is reflected perfectly across the y-axis. The next slide covers the topic of non-rigid transformations, which are known as stretching and shrinking. So all the transformations that we saw before did not transform the shape of the graph itself, but rather just shifted it left, right, up, down, or reflected it across the y-axis or across the x-axis. Now we're going to see the so-called non-rigid transformations, which cause the shape of the original function to change. So first we have the vertical stretch or shrink. So this happens when you have y is equal to f of x, and you multiply f of x by a value. Let's call it a. So y is equal to a times f of x. So the first case is when a is greater than 1. When a is greater than 1, or it could also be negative, that would just also cause a reflection, but that's a separate topic. For now, let's just think of the cases where a is greater than 1. What's going to happen is that you get a vertical stretch. So for instance, here we have x squared in blue in figure 1.38. And then we have y equals 3x squared. So notice that what's going to be affected, again, is only going to be the y coordinate. So every y coordinate will be multiplied by 3. So notice that 1, 1 becomes 1, 3. 2, 4 becomes 2, 12. So the x coordinates stay the same, 1, 1, 2, 2, but the y coordinate is multiplied by a factor of 3. So obviously this is going to make the graph go up quicker, so to speak. So it's going to stretch it vertically. So whenever the value a is greater than 1, as we see here, you have the vertical stretch. Notice that here you have the coordinate x comma f of x, and this new coordinate would be x comma a times f of x. Now we're going to look at the case where a is a value between 0 and 1, such as 1/3. So what happens when you have 1/3 x squared? So y equals 1/3 x squared. Well, you have a vertical shrink, because every y value will be now 1/3 of what it was. Notice here that if you have 3, 9 for x squared, for 1/3 x squared, it's going to be 3, 3. So 9 divided by 3. Likewise, if you have 2, 4, now the new coordinate would be 2, 4/3. So notice that, again, it only affects the y coordinate. Next comes the horizontal stretch or shrink. So the word horizontal already indicates that it's going to affect the x coordinate. So notice that in this graph to the left, figure 1.43, they're showing us the horizontal shrink of y equals x squared minus 4x by a factor of 1/2. Now with x, everything seems to work backwards. So if you want to shrink it by a factor of 1/2, you would actually have to multiply x by 2. So notice that the function y equals x squared minus 4x would become y equals 2 times x squared minus 4 times 2 times x. So now we multiply every x by 2 if we want to shrink it horizontally by a factor of 1/2. If we wanted to shrink it by a factor of 1/3, then we would have to multiply by 3 and so forth. So what happens now is that only the x coordinates are affected. Notice that all the y coordinates remain the same. 5 is 5 here as well as here. But the x coordinate, which is also 5, now becomes 5/2. Same with 4, 0. Notice that 4, 0, y is not affected, but x is half of what it used to be. So next we have the horizontal stretch. So in this case, the blue graph is y equals x squared minus 4x. Here they have it wrong. The blue graph is y equals x squared minus 4x. And the red graph would be y equals x over 2 squared minus 4 times x over 2. So notice that if you want to stretch by a scale factor of 2, you actually have to divide x by 2. So again, with the x's, it works backwards, right? If you want to stretch by a factor of 2, you divide by 2. If you want to shrink by a factor of 2, you multiply by 2. If you want to move it right, it's minus. If you want to move it left, it's plus. So keep that in mind. Now, notice that the y coordinates stay the same. So 5, 5 becomes 10, 5. And notice that only the x value changes again. Negative 1, 5 becomes negative 2, 5. 4, 0 becomes 8, 0. And 2, negative 4 would become 4, negative 4. So in general, if we want a horizontal stretch, we would have to multiply x by an a value between 0 and 1, and the function f of x becomes f of a times x. We continue with example 1.24. And it says the graph of y equals f of x is shown. Sketch the graph of each transformation. So first, we have y equals 3 times f of x. So notice that this is a vertical stretch, right? 3 times f of x. In this case, every x coordinate stays the same, but y will be multiplied by 3. So for example, 3, negative 1 would become this point here. 3, negative 1 would become 3, negative 3. This other point, 1, 1 would become 1, 3. So it would be there now. 0, 0 would stay the same because 0 times 0 is 0. Negative 1, negative 1 would now become negative 1, negative 3. And then finally, negative 3, 1 would become negative 3, 3. So you do that, and now we would be ready to join those dots to see the graph of this function, which would now be stretched by a factor of 3. So I'm going to try to draw this very carefully. And that would be more or less the transformation of letter A. So for the others, what I'm going to do is explain what's going to happen and then change the graphs. So for B, we have 1/3 f of x. So this obviously would reduce all the y coordinates by 1/3. X coordinates would stay the same. For C, we have f of 3 times x. Now remember that this works backwards, right? So every x coordinate is actually going to be 1/3 of what it was, and every y coordinate will stay the same. For example, 3 comma -1 would now be 1 comma -1. And then finally, if we have y equals f of 1/3 x, every x would be multiplied by 3. The y coordinates would stay the same. So for example, 3 comma -1 would now become 9 comma -1. So let's look at the graphs. So for A, we can notice that all the x coordinates stayed the same, but the y coordinates were stretched by a factor of 3. When it's 1/3 f of x, the x coordinates remain the same, but the y coordinates were reduced by a factor of 1/3. Then when we have y equals f of 3 times x, the y coordinates stay the same, but we have a horizontal shrinking with a scale factor of 1/3. And finally, when we have f of 1/3 x, what we get, and this is wrong here, by the way, this is not the right notation. This should be f of 1/3 x. And what we get is a horizontal stretch by a factor of 3. So in this case, all the y coordinates stay the same, but the x coordinates are multiplied by 3. So now we're going to take a look at example 1.25, which will be the last one on this video. And it says, describe the sequence of transformations performed on the graph of y equals x squared to obtain the graph of y equals 4x squared minus 3. So think about this, and we'll see if you get the right answer in the next slide. Ready? Here we go. So first, you had y equals x squared, then y equals x squared was stretched by a scale factor 4, and you get 4x squared. And then there was a vertical translation of 3 units down, and you get 4x squared minus 3.